So let's look at applying this method to the particular problem we discussed. And so let's remind ourselves of the small parameter beta, which is this non-dimensional damping rate, which is going to be very small. And the basic idea of the perturbation expansion is that we express the solution in terms of a series which involves corrections. So we have V0 of tau. This is the solution without any damping. And then when we account for damping, then we have corrections. And since damping is small, we have successive corrections. So that is the idea of a perturbation expansion, that we successively correct for things that we had removed from the problem to reintroduce a small amount of damping. And so V1 and V2 and so on are corrections which are going to be obtained by a systematic method. And so they are multiplied by these functions of beta, which is beta, remember, is a small damping parameter, non-dimensional damping. And so in general, we introduced the idea of what is called the gauge function. And so this gauge function essentially determines the magnitude of damping, or how important damping is. And so we have various functions, epsilon 1, epsilon 2, and so on, which are functions of beta. And depending on the problem, these functions need to be chosen so that they represent the physics that is occurring in the problem. But all of these functions, they will serve the role of gauging how important the correction is for any given value of beta. And they are going to vanish as beta vanishes. And so as damping vanishes, all of these corrections will vanish. All right? But they vanish at different rates. And so, for example, in the present problem, the gauge function epsilon 1 is going to be chosen as beta itself, and epsilon 2 is going to be chosen as beta square, and we can have higher powers here. And so as beta goes to 0, these terms vanish at different rates. So this term vanishes much more rapidly. This term vanishes less rapidly. And so if beta is very small, then of course it's only the first term that is going to matter, and so on. So we are writing the solution in terms of these gauge functions that have been chosen. So the solution is the undamped solution plus corrections at different orders in powers of beta. Beta power 1 times V1, beta power 2 times V2 here of tau. And these are solutions that need to be found. V0, V1, V2 are solutions that need to be found, and we can go as much as is needed, and so on. So this expansion, this is the asymptotic expansion, is going to be substituted in the ODE that we have, and we are also going to substitute this in the initial conditions that we have for the problem, and that will give us an expansion of the equations and initial conditions at various orders in beta, and it is that we're going to use to determine the behavior at various orders. And so that is the process that we're going to now discuss. So let's apply this idea. And so for this, let's use a shorthand. And so we will put a dot over a function to denote the derivative with respect to tau. So this tau is non-dimensional, and so this is not the same time derivative as we had before. It's non-dimensional time derivative. So let's not forget that. All right. So we have, we can take the derivative of the expansion. And so we have the first derivative in terms of now derivatives appearing on each of these functions. Beta powers just are outside, and we can take second derivative, and we have second derivatives v0 double dot, v1 double dot times beta, v2 double dot times beta square, and corrections truncated here at order beta cube originally, and therefore that is carried through. And so we're going to substitute this in the differential equation, and to remind you that the differential equation itself has this term involving beta. Remember, beta is the small parameter. That is why something is changing relative to beta not equal to 0, beta equal to 0. And so we're going to now substitute these expansions in here, and then we will collect terms at various orders in beta to obtain the equations at various orders from the equation and from the initial conditions. So let's proceed in that path. So this group of terms here is the expansion of the second derivative. V double dot is expressed here. 2 beta times, this is an expansion for V dot. And then finally, this is the third term in the equation written here, equal to 0. And so now what we can say is that at different powers of beta, we can collect all the terms that show up. And so the coefficient which has power 0 of beta, which is what we call order 1, is v0 double dot, and this of course shows up with beta, so this doesn't show up here. This is a term again which has no power of beta. So this term and that term go here as coefficients at order 1. And then there's nothing more, so that must be equal to 0 at order 1 in the equation. And so likewise, we can go to order beta. So we pick up this term here. Here now we have 2 beta times v0 dot, so we get 2 v0 dot. We move that to the other side, and so it becomes minus 2 v0 dot. And then here we have another term which is beta times v1. So at order beta we have v1 showing up in the equation. And so this is the equation at order beta. And likewise you can see the equation at order beta square. And so we can now do the same thing for the initial conditions. Remember, the initial condition is that v0, v at 0 is equal to 1. And so we expand v in its asymptotic expansion. And of course, right now it's all very straightforward. We just have to collect terms at various order. So at order 1, power of 0 for beta, v0 of 0 must be equal to 1, the initial condition that is given. And then the initial condition at higher order becomes that they are equal to 0. And likewise, we have a straightforward calculation for the second initial condition. The time derivative of v0 at 0 is equal to 0. And that's the expansion. And so at various orders, we get these very simple equations that the derivatives of all these functions at 0 are all 0. All right, so this defines the system of differential equations and the particular initial conditions they have to satisfy. And then the next step is to solve these. Okay, so let's solve the equations that we encounter at various orders. So at the leading order, at order 1, we have this differential equation, which is the spring mass oscillation differential equation with no damping, with these initial conditions that displacement is 1 and the initial velocity is 0. And so that's a problem which we can easily solve, and we can say that the solution is, of course, the homogeneous solution here, sine tau plus cosine tau with arbitrary constants, and noting these initial conditions, since initial displacement is 1 and initial velocity is 0, we can find those two constants, and that gives us the solution in this cleaned up form that v0 is equal to simply cosine of tau. And so we're going to need the time derivative of this later, and so we note that time derivative here. All right. And so now proceeding to the problem at order beta, this is the differential equation where we have the left-hand side is the same operator on v1 as we originally had on v0. This is the same differential operator acting on v1. But now this is an inhomogeneous problem. We have a right-hand side, which is minus 2 times v0 dot. This is a known right-hand side because we already have solved for v0. And so we have that already solved. We can substitute that. And so this right-hand side is 2 times sine of tau. And so if we look at this equation, we would recognize the fact that the solution sine of tau is a solution to the left-hand side of this equation and is appearing on the right-hand side. And so this is like a mass spring system which is being forced by an oscillation in force which has the same frequency as the natural frequency of the system. And so that is called a resonant term because it has the same frequency as the solution to the homogeneous problem. And mathematically we call such terms secular terms. So here we now have a forced resonance, a resonance or a secular term showing up in the equation. And the initial conditions for the problem are, of course, homogeneous as we had noted by the expansion of the initial conditions. And so then the question is, what is the solution to this? Well, there are a number of ways in which we can solve this problem, this inhomogeneous problem. One method that we have learned is the method of variation of parameters. We can apply that here. And two things we need to recognize is that the solution V1 is made up of the homogeneous solution plus a particular solution, and then we can find the particular solution and the homogeneous solutions. We can observe simply that the particular solution, in the case when it's forced with a secular term, is going to be made up of A1 times tau times sine of tau and A2 times tau times cosine of tau, and we can substitute this particular solution in the differential equation and collect coefficients at various powers of sine and cosine and so on, and we can deduce by a straightforward logic that we have discussed before that the unknown coefficients A1 and A2 have these values, and homogeneous solution can be found very simply as saying that it is some arbitrary constant times sine of tau plus some other arbitrary constant times cosine of tau, and then imposing these initial conditions. Overall, we can find that the solution is given by this. This is the total solution, homogeneous plus particular solution. And we're going to need its time derivative, so we can calculate its time derivative. The first term differentiates to cosine. A second term, when we differentiate, we get two terms. This last term cancels this one. So overall, we have tau times sine of tau as the derivative of v1 that is needed later on. And so the problem at order beta square is given by this equation that we had recognized before. And the right-hand side now is known. Again, is the same operator on acting on V2 forced by this right-hand side, and the initial conditions are again homogeneous for this problem. And so again, we can apply a method like what we have talked about before to obtain the solution in this form, that V2 is given by 1/2 tau squared times cosine of tau minus tau over 2 times sine of tau. And so at this stage, we can assemble all these and take a look at the solution that we've got and interpret what we have. So assembling these solutions that we have obtained, V of tau, remember, is a perturbation expansion. This is the leading order term. This is the first order correction in beta. This is the second order correction in beta, and so on. And we have already evaluated these, so we just substitute them here. And then once we have substituted them, we can reorder this. And what we're going to do is we can see that there is a cosine of tau here. Here is another term with cosine of tau. Here is a third term with cosine of tau with other coefficients. And so we're going to all factor them together. And so in this curly bracket, we have collected all the terms that involve cosine of tau. And then we see here that there is a sine of tau, and so on. So here in the second term, we have collected the coefficients of sine of tau. All right. So we can interpret this solution. This is the solution without damping, and these are corrections associated with damping. And when we reorder it, we can see that we can say that the cosine tau, its multiplier here is not constant, which is the case when damping is not present. So if we think of this as an amplitude associated with cosine, that amplitude changes in time, and in fact, for small damping, it decays in time. This term is larger than that term, and so relative to 1, it decreases at a rate which is given by beta. And there is a smaller correction which is also at a sine of tau, which means that the phase of the oscillation is shifted a little bit relative to a pure cosine because of the presence of the sine term. So that's an interpretation in terms of a successive correction. Of course, as we look at it, we can see that this successive correction idea is appropriate provided terms that appear at higher powers remain small compared to terms that appear at lower powers. And so we can compare terms at higher power compared to at lower power, or this relative to this, and so on. And we can deduce that this successive approximation will remain valid if beta times tau is a number which is less than 1. If it is small compared to 1, then all of these corrections will remain smaller compared to the previous terms, and so we will have a very good approximation. And so the solution is valid provided beta times tau is much less than 1. Then we can truncate this at low powers. And so which means that the solution is valid for times, just rewriting this, times, non-dimensional times, much less than 1 over beta, which in terms of original physical time, if we interpret these back in terms of the original dimensional variables, it will say that the physical time is much less than the damping time that we had estimated before. So provided time is much less than the damping time, not a whole lot of damping would have occurred, and therefore the effect of damping is a small correction and can be computed in this way. And so another way to say this is that this perturbation expansion that we have obtained is not valid for times that are large, that are arbitrarily large, in particular large or comparable to the damping time scale. This solution is valid for short times compared to the damping time scale. And so a natural question then is, can we then construct a solution, an analytical solution, which is valid for much longer times, such that the cumulative effect of damping can be described? And so this can be done, and there is a variation of what we have talked about. It's called method of multiple scales, which allows us to extend what we have described here to do what we would like to be able to do. So that would be the topic of further development.